Hello, everyone. I think I may have chosen a little bit of a catchy title, right? But let's see if I can meet the expectation here, right? So today I'm gonna maybe try to cover at least one topic we have been working for almost last 5 years since I started and as an assistant professor, right? And then I think perhaps one of the pillars of my efforts, which got to me through the tenure, maybe, right? Who knows? But so let's look at that, right? So I guess we have been using so many resources, right? I always get complaints you're not using it efficiently. So I want to say I'm doing my best, right? And apologize for not using as effectively as I can. So we also have a unique property, I think, that we are using a lot more CPUs than GPUs as well, right? And then maybe, hopefully, I can elucidate that. And maybe I don't stand, or I think we are using more CPUs, but I'm not sure if we are, right? So let me look at some of the things we have been doing, right? So I want to cover sort of a broad set of topics on how we can do all weather sensing and then how do we build autonomy at large with this all weather sensing, right? And then maybe even go to sensing, and the last topic maybe we'll skip, but we'll see if we get to the time, right? So let's take a look, right? I think this is the first where we tried to start with in 2017. We're trying to build a perception system which can work in all weather settings, right? And I'm going to get to what it means, right? And this was done by a lot of cool students. A lot of them are undergraduates. Two of them are PhD, right? And they all contributed to all these publications, right? And this is the webpage if you want to go check out what we are doing here. So what is the problem, right? So you see autonomous driving, I guess, as I say, it's the new black, right? I think everywhere from the small cars, there is a local company called TU Simple. It's trying to make autonomy for trucks, right? I think truck driver and finding truck driver is a really hard problem, and they've been trying to do that. There is a really good friend of mine sort of trying to push autonomous tractors at John Deere / Blue River, right? I think actually the student who worked on it actually graduated and joined them, right? So I'm glad. And there are like other use cases, right? In general, broad stroke autonomy in the driving has lots of applications, right? And so towards this, right, I'm gonna maybe discuss and explain some background on autonomy and how the world is and where the world is today a little bit, right? So there are like 5 levels of autonomy, right? Level 1 is some of the things we know, like cruise control and lane tracking, right? Okay. And then there is self-driving, right? And there are 4 levels, or within that 3 levels, right? Just to give you, nobody is above level 3 right now, okay? Like Waymo just gets to level 4, right? So nowhere close to level 5. I see there's some bugs in the slide, but maybe just Mac versus Windows. Any case, so nothing gets to level 5. Tesla is also level 3 today, right? So you need to get to level 5 when you can truly rely on these things, right? And these are the levels of autonomy defined, right? So what is preventing these things to get to level 5, right? Okay. So let's get to that, right? So let me give you an example, right? So this is how you can imagine driving in the fog is, right? So I want to maybe make one thing more precise here, right? The entire reason for this self-driving cars and whatnot is precisely to be safe, right? If they cannot do better than human, then what's the point, right? Like human already knows how to drive the car, right? If you want to get something which is beyond sort of human, right? Okay. And this is what happens when we sort of are faced with inclement weather, right? We sort of end up colliding. I don't know, maybe play this video, but let me show the next one. That is really cool, right? I think, and this is in the sand, right? I think if you go to Vegas or somewhere close, you might end up getting into this situation, right? People overtaking without really any vision, right? And it's like almost impossible to drive, right? So this is where we want these cars to drive, right? That is what it truly means for a technology to create an impact, right? Okay. So how do we get there, right? So, all right. So let me look into now the sensors used to getting there, right? So the most common one, which everybody probably have heard in the audience, is LiDARs, right? So I'm just showing you this really complicated dotted figure. It seems like somebody drew a graffiti which just dots, right? And that's what basically what your LiDAR does. It sort of captures your environment using dots, okay? It's called point clouds, right? And I'm sure a lot of you know, right? I may be just saying useless things, but the thing is that you see a lot of dots and you see things at different distances, right? And this is your ego vehicle, right? Ego vehicle as in the vehicle where the LiDAR is mounted, right? Now, as you increase the fog, you start losing visibility. Like the lack of dots is the explanation for that, right? Okay, and if you keep increasing fog, you just pretty much don't see anything, right? You see the more dense of reflections coming back from the vehicle itself, right? Which means that your lidars are truly blocked, right? Now, if this may not make sense, I think it's okay. The concrete messaging is following, right? That the wavelength these lidars use, right, is very small, right? Okay, and that is smaller than the particles like dust and other things, right? And therefore they block all of the visualization of what you can see in the environment, right? So that's physics, right? Nobody can beat physics, right? Even Elon Musk can't beat physics. Okay, so this is where I guess, and of course camera definitely can't help you there, right? So let me come to something which I think there is a lot of debate on, which is radars, right? Okay, so what do radars have different compared to lidars? The fundamental difference is the wavelength they use. They use a much larger wavelength compared to lidar. And what it helps is that it can then penetrate these particles and only get reflected by larger objects, right? So this is the fundamental idea behind why I use radars, right? There are lots of problems with radars, right? I can give you all the good things about radars, right? It can even do this, right? It can look behind a car if you want to be precise, right? I think I've been seeing some really cool work coming up in this space as well, right? And there is a long range of sensing it can do. So let's look at an actual scene, right? And this is how your LiDAR point cloud looks, right? So you can clearly see that car and the box indicates that that car is there, right? And this is radar point cloud. This is the fundamental problem with the radar, right? It basically goes away from the particle nature of the light to a wave nature, right? And what it means by wave nature is that so this is how light reflects, okay? It reflects in all direction, right? So every point gets reflected back at some level. This is how wave reflects, right? It has purely specular reflections, right? Because of this, you don't get a lot of point, right? And this is why there is a large debate whether to use radar or not, right? Does it add value or not, right? And this is what we set out to investigate, right? How can we use radars to make them give outcomes like lidars, right? That was really the charter of the research, right? So let me just get to our research vision, right? I think this is also funded by NSF. I think the larger the size of the banner, the larger they have funded me, right? Okay, so I have like proportionally chosen their factors, right? Any case, right? So Texas Instrument funded very limited, right? And that's why, but they gave us the key component in this, which is the radars, right? So I'm glad they gave us a lot of their early radars, which weren't even available to the market. They gave us early prototypes. So I'm glad of that, right? And that enabled all of our research, right? So what was our goal? Goal was to get this safety and reliability. And can we use these radars to enable that, right? And three fundamental questions we had, right? The data quality is very low. How can you improve that data quality? How can you get semantic understanding? And how do you get contextual information, right? I think this may seem a lot of things, right? I'm gonna maybe now just focus more on how we went on use NRP, right? So we have three particular papers. I think the slide is broken. Sorry, folks. I think it was supposed to go other way around. In any case. So each of these three papers deliver on one of these aspects, right? The pointillism delivers high quality data. Radar SegNet combines radar and cameras, right? And our fiducial provides contextual understanding, right? For example, if there is a stop sign, right? If there is a red light, right? All these things which you think are very hard to detect for radar, we even show that you can detect those, right? So this is an example of pointillism, right? I'm gonna just show a demo, right? And this is a real-time running demo. You see how LiDAR is predicting distance wrongly for this car, but radar has consistently predicting right? And this was sort of covered widely by the local news channel and New York Times and whatnot, right? I don't remember either. But let's see what we did, right? So we did build this rig, right? It's a lot of cool 3D printing. And we attached this rig to my car, right? It's a really amazing Mazda, right? And from a decade old when I was a graduate student, right? And that's why we don't care, right? What happens to that, right? So this is the Mazda I drive, right? Okay. And we basically collected lots of data, right? Actually, just to give you a sense, right? A lot of experts may have seen there are a lot of data sets coming out from different companies like Waymo and others, right? A lot of them use these very, very low quality radar, right? And therefore, those data sets are useless for doing like the things which we are trying to do, right? Like LiDAR, like radar, if you want to do that, you need a high quality radar, right? And then it's not that expensive to get this high quality radar. It's really, really hard to use. The amount of data it generates, the pipelining software does not exist, right? So a lot of people just use whatever is easy to there, right? And use it, right? And because we are wireless expert, we knew what radar we want to use. And we just had to build a lot more software pipelining to get this data set, right? So a lot of undergraduate students built it, right? And the worst part is that since we collected our own data, we had to label that data as well, right? Like it's just really expensive to even label data, right? And so I'm going to go over how we use now NRP. So here's what we did. We got a lot of this data. We hired a whole bunch of undergraduate students, right? And we put all of our data on the NRP and we launched these VNC browser type desktop machines, right? So everybody was assigned a folder or two and they just went up. We had a tool our own in-house and they labeled different LiDAR data sets, right? I'm going to show an example of how the labeling looks like. You have these dots, you do overlay of LiDAR as well, and then you draw a box around it, right? Okay. So a lot of students, a lot of undergraduate students help us with this effort, right? I think it was among us. In a month, we had like somewhere around 20 students working on it, concurrently doing all this labeling, and all of that was backed at a single location, right? And the great thing was they had a shared volume which spin up. Everybody can just launch a desktop browser, right? And do their work, right? So that was great for us, right? Now, I think this was like slightly unique. I'm sure like all of us have used NRP for the typical use cases of once you have a data set, once you have labels, right? How do you then do AI ML training and how do you do optimization and how do you scale up your flows, right? I think those are the natural things we did, but this was slightly unique to what we did in our case, right? And the interesting thing is that we were, for some not so great reason, we were using MATLAB. So we had to launch a image which has MATLAB pre-installed in it, right? And that took a long time to figure it out, right? And I think John and Tom and their team sort of helped us build this image, which had pre-installed MATLAB in them. And then the student would spin up that server and that VNC will launch that browser and you're directly on a MATLAB and you can start labeling these things, right? Okay. Don't ask me why we use MATLAB, right? Okay. We just built all of our pipelining with MATLAB, right? And we just continue to stay with it. I think there are a lot more Python and other cool tools out there now, right? Okay. So basically, all of this sped up our entire progress, and all of these papers and the impact is at some level not just function of the student, but also the resources we got from NRP, right? Okay. So I'm gonna maybe go to the next switching, right? So the thing we spent a lot of time is that we built these good bounding boxes with radars, right? And when we went out and asked industry, hey, do you need 10 centimeter accurate boxes for a 5 meter by 5 meter car, or do you need 20 centimeter accuracy, 30 centimeter accuracy? Nobody knew the answer, right? They just came up with random numbers. We went to this IEEE VTC conference, right? We have no precise numbers, right? So the only way to evaluate this is that you build this sensing and then drive the car using that sensing, right? We'll know how many collisions you made, right? How many hits you made, right? Okay, right? Now, don't do it in real world, right? That is the second thing, right? And this is where we shifted to doing this in digital twins, right? So, of course, maybe you know about Carla, but we used, so this is the question, right? How do we prove that we have built something which is reliable and autonomous, right? Okay, with all these new tools, right? So this is where we created a high fidelity simulation tools, right? Now, the problem with these simulation tools is that on one side, you can go to something called HFSS. This is like ANSYS HFSS. Just to give you an example, right? To simulate a room of 5 by 5 meter, it takes a day if you want to do very, very accurate FDTD simulations, right? Okay. And that's like pretty much solving Maxwell's equation for every single volume and so on and so forth, right? And it's not like NRP can do that any better either, right? It's just a fundamentally very hard problem to do simulations accurately at this frequency, right? Because of the wave and the diffusion and so many things to consider, right? So first, we had so much large scale real world data collected. We painstakingly created or used Carla models, right? So Carla also has a radar model, right? Sadly, all the radar models out there sort of don't work well, right? Okay. Either they are too slow or they don't work well, right? Like the highly accurate one are extremely slow and the inaccurate one are too inaccurate, right? Or they are fast, but they're inaccurate, right? So we went and built our own radar model, right? A sensor model, right? And we basically took lots of real world data we collected in the last phase, right? And we basically, I can show you an example, representative example of how our simulator shows the cars. This is called a spectrogram, right? On x-axis is your x horizon and y, it's like a looking from bird's eye view, right? So what you see is that they are very, very similar, right? And we did a lot of development of radars, lot of material property understanding and a lot of these things, and experimentally finally built a tool which accurately mimics radars, right? I think this is actually a very cool tool, right? I think a lot of people are right now licensing or working with us to license this tool, right? In case. So just to give you, if you're using Carla's radar, don't use it. It doesn't work, right? Okay. It's super inaccurate. They just took LiDAR and just randomly dropped few reflections and it did a few things which doesn't make sense to me, right? Okay. Maybe they came up with something, but the precise thing is that we built something called Shenron. Okay. This is a paper which is going to be up at upcoming ICRA, right? I'm going to present, and this is what is really popular right now. So we have a very, very accurate Shenron, which is, I think, a radar sensor model, right? And what we did is that we plugged that into Carla, right? Okay. And now you can pull this from us, right? And you have an accurate radar, camera, LiDAR, right? And all of that you have in Carla. Now, what's great about this? Why are we doing this, right? So in Carla, you can create a scene, right? Okay. So just give you an example, right? You can create a scene like this, right? So that you don't have to drive around with my radar and just bump into people, right? Okay. You can just bump in the simulator and make it perfect as well as you can, right? So this simulator now has all the sensors you want, right? And you can place multiple radars, you can place them various locations, you can do whatever you want here, right? And this is what we did with the NRP Next, right? Or Nautilus, right? So what we did is that basically you can see this car, right? This collision, right? That was cool, right? But it was cool in the sense that it was in the simulator, right? Which doesn't happen in real world, right? But the point is that this car is driven entirely by radars, okay, right? And that's why it's doing some weird things, right? It's driven by radar plus cameras, okay? That's it, okay? So I don't have any algorithmic details in the slides, but I want to focus on what we did and why NRP was so cool for us, right? So with Carla, the problem is that running these simulations, each time you train a model, you have to drive a lot of scenarios, right? And driving all these lot of scenarios, getting data, how well we did, how well we didn't do, right? Or even collecting data, right, was a nightmare, right? And this runs extremely, extremely slow if you have to run it in your local compute, right? So we created massive flow of like launching GPUs, and automatically we had a bash script. Every time we had a new model, a bash script would launch. It would spin up 210 jobs. Each of these jobs pretty much will be thrown at the A10 GPUs, right? And what used to take a week to us, right, in our lab, right? We had some our own GPUs, right? It became an overnight or even 4 hours now, right? Okay. To basically collect that data, right? And more importantly, even the funny thing is that once you have a trained model, it takes a week or at least 4 days to train or see how well it is doing, right? Even that reduced to few hours, right? So our iterations became really, really rapid and really fast, right? I think we are pretty much close to finishing this work and publishing this as well, right? Like I think this, is truly where we really, really benefited from the efforts from the Nautilus, right? I want to maybe show you one cool demo of this, right? So this is what I think our final system looks like, right? So this is LiDAR or radar, right? Okay. And this will be the scene of the camera, right? Okay. And we keep playing these to figure out how well we are doing and so on and so forth, right? So this is like the car driving with radar, right? Okay. I don't know what these blips are, but I think maybe just we are running out of frame sync, right? Okay. But the point, I think the previous demo maybe was cool, right? As you can see this car colliding, right? Okay. But we're still working on improving algorithms, right? But it's all possible because of NRP for us, right? This is another, actually, yeah, this was the one I was looking for, right? This is another cool video where we sort of continue from the previous scene, and you can see how LiDAR has so much higher quality. And radar has a good quality and it can see most things, but it still has to do a lot of characterization and whatnot, right? Okay. So I'm gonna maybe I can stop here and or maybe take questions, right? And let everybody go early for lunch, right? I think we have had enough load of cool ideas, right? I think let's take a pause and yeah, questions. Go ahead.
So Dinesh, I have a question.
Yes.
My first Tesla had radar, and then as well as visual.
Right.
And Elon says we don't need radar. Wow. I mean,
So-
it seems like you're showing that it's actually really essential.
Right. So I think, so let's, just to give you an example, right? The early first generation of Teslas, which had, sorry, somebody saying something? Oh, Mike. Okay. All right. So the first generation, so the question was, the first generation of Teslas had LiDAR and they radars, and then they dropped it, and then now they have brought it back. I just want to give you this entire story, right? So in the first generation, they use these LiDARs, which are very, very low resolutions, right? And they barely could do like just detecting a car in the blind spot or things like these, or detecting a very, very close wall, right? Okay. Those are the things they were doing, right? And then they realized that ultrasonic sensors can also do the same things. It's just not like, it's not adding a lot of value, right? Okay. And this was because this was a radar which was a very, very low resolution, right? And it was a single chip, one transmit, two receive, right? Or I think that was the sort of they were using the version, right? Then they've spent a lot of time using cameras, right? Just to give you a sense, Tesla is also level 3 right now. It's not close to, I don't know, if you have tried Waymo, then you would see an entirely
Oh yeah, Waymo's very much better.
much better, right? You see, right? Exactly, right? And that's because I'll come to that as well, right? It's also, Waymo is also just close to level 4. It's not still level 5, right? Okay. But in any case, let me maybe finish the point. Next generation, which recently Tesla has, it has a 2-chip radar on it, right? Which is basically 6 transmit, 8 receive antennas, right? It's pretty close to the chip or the framework of radar we are using, right? Okay. I think we have had lots of discussion and communicated these results to them as well, right? And they have seen some of our promising efforts, and then they augmented their radars to use many more transmit and receive, right? In the first generation, they had only few transmit and receive, which was not doing really well for them, right? The next generation now, which will be the next, what is it called, FSD 4.0, right, will have radars in them, and they will have a high resolution radars, right? And let's hope, I think I'm very curious how that experiment plays out.
Probably
And-
it was also Mobileye integration problem.
Right.
The software stacks were different.
I see. Yeah,
Yes,
interesting.
So the first generation had Mobileye.
Yes.
And,
Got
so
yeah.
that-
Sorry, you had another question, or somebody had another question? Yes.
I have a question. So regarding the millimeter wave radar you mentioned, what's
Yeah.
the cost compared with the current LiDAR?
So I think I can give you the cost of millimeter wave radars today is roughly, with everything included, somewhere around $70, right? Okay. This is for the entire board and everything else you would like to need for one radar, right? Okay. It's at least maybe like, I think last time I bought some LiDARs was quite expensive, but I'm guessing at scale, they would also cost somewhere around like $700 or $800, right? Just maybe a factor of 10 cheaper, right? And the other benefits with I think the more important point I want to maybe make is that it's not to say that we should go away from LiDAR, but it is to say that it's about safety and reliability. We should have every possible tool at our hand to be used, right? So I think there is a lot more like, every single dollar extra, if I ask somebody to put, right, in a car, they are like, oh, what are you saying, right? It's, any case, right? I think it's a different story. But the point I want to make is that LiDAR, radar, and camera, it should be all used in unison, right? And then while one can argue, and our own paper argues that we can use camera and radar and it can do well enough, right? I don't think we should play with safety, right? That is my take, right? It's all about, like, if one sensor dies or it does report uncertain information, it's better to be safe than sorry, right? But yes, does that answer your question?
Yeah. Thank you.
So there is a SWaPC analysis on our webpage if you want to see size, weight, power, right? And so we have been thinking of sensing for different types of small drones to large drones to like full scale autonomous cars, right? What works well and what doesn't work well, right? I think you can find a lot more information on the webpage we have.
Thank you, speaker again.
Thank you.